Sure. Sure. So my name is Bill Howe. I co-lead a place called the eScience Institute at the University of Washington that was built to really explore data-intensive science, so sort of big data in the sciences. And so we spend a lot of time working with oceanographers and astronomers and so on. So I think representing academia on this panel, there's a few things that I maybe wanted to call out. One is, the talent question, I think. So sort of building pipelines between academia and industry, sort of figuring out what sort of skills are being required and what skills we're actually teaching. Both of these things I think are changing pretty rapidly, and we're putting a lot of thought into how to do that better. I'll give you an example of that is where we're finding that folks coming up in disciplines that are not traditionally associated with some of these industry data. So let's say data analytics and increasingly perhaps Internet of Things jobs are coming from fields other than, say, computer science, electrical engineering, and so on. There may be physicists or there may be astronomers, and they have a strong math background. And they produce far more PhDs than there will be faculty positions or research positions. Yeah. They said, you're all set, and I believe them. So it says on, and there's a green light. It says on, there's a green light. Volume was down, I guess. As I was saying. So I guess I'm representing academia. I mentioned this place called the eScience Institute. We do data-intensive science in general, and there's some connections, I think, to IoT, one of which is talent. We're seeing people coming from non-traditional backgrounds moving into this space, both in data science and perhaps in Internet of Things. So, for example, astronomers that are going to start big data startups because of their depth in mathematics. And the number of PhDs we produce in these various fields is far, far more than the number of research positions available. And so this is potentially a good fit, right? They get to spend sort of some number of years studying the sciences, and then without sort of having to give up on a career later. Another area we see is just in the sciences themselves. There is sensors are getting cheaper just for those applications, just as they are in these applications, and the trickle down of technology is not always as clear. So we're really trying to explore sort of new ways to get them access to the data to the data that they're acquiring. And so as my PhD is in computer science. As a computer scientist, I'm actually sort of embarrassed that the engineers seem to be able to sort of acquire this data and build the sensors to actually get the data from the world, and the bottleneck has become the analysis of that. That seems strange to me, right? Because once it's ones and zeros, it should be easier than actually sort of pulling the data out from the world, but they're in some sense ahead, and so that's surprising to me. And then one aspect of that I'll ask the audience maybe as part of this whether you see this as a problem, but one thing we think hard about is sort of the long tail of science, which is the smaller and medium-sized labs, relatively smaller number of researchers. Certainly they don't have no IT department. They have exploding data needs and exploding sort of management of sensor networks needs. And trying to think about how tools can sort of scale down to that level and be picked up seems to be important. And there's perhaps an analogy here with smaller companies. There's perhaps an analogy here with the homeowners who are doing this stuff. But that's maybe a question for the audience of whether you see that as a strong need. Because obviously, if you're talking about factory floors, they have an IT department to invest in, and can maybe soak up some of the stuff. And then so talent, sensor networks themselves, and then scaling down. Maybe I'll stop there and pass it on. Yeah, sure. So this was founded in 2005, 2006, and funded in part by the state of Washington in 2008. More recently, we had a couple of big grants out of the portfolio. One is from the Gordon and Betty Moore Foundation and the Alfred P. Sloan Foundation joined together and gave a joint award to Berkeley, New York University, and University of Washington to build what they call a data science environment. And the idea here was really to invest in sort of second-order change to affect really institutional change to make data-intensive science the norm rather than the exception, right? So this is, as opposed to giving money to the splashiest data science projects they could find, they really wanted to sort of see if they could sort of change the culture fundamentally, and the eScience Institute is charged with facilitating that. So this has to do with things like creating career paths for data scientists on campus when otherwise they would have gotten spun out to industry as soon as they graduate to sort of stay around and work on things like astronomy and oceanography. It has to do with changing education pipelines. It has to do with making software development kind of more like what we like to think happens in industry. It has to do with reproducibility, which has come up a couple of times in the conversation already. And then we also think about working spaces and culture, actually, which is a bit of a abstract one, but the idea that there might be the physical location actually affects what kinds of projects you can take on in this data science space. We think a little of that. And then these are the working groups I'm listing off here. The sixth one here is ethnography and evaluation. And the idea here is that the wind is kind of blowing this way anyway, so we could actually sit back and do nothing for 5 years and probably look good because data-intensive science became more prominent than it was, and we want to make sure we inoculate ourselves against being complacent about that. So that group's charge is to really make sure that we're setting aggressive goals and meeting them. And so that's been our mission at UW, and we hope that some of the programs that we spin up, some of the ideas that we have will be picked up by other universities and sort of adapted for their campuses.
Thank you. Yeah, why don't you go ahead to the next slide, the first slide. So I only have 2 slides, and I just wanted to give you a little context of where I'm coming from, where my comments are coming from. Obviously, I'm at Huawei now, and I'm the head of the Media Technologies Lab. Huawei is a networking company, so we have some perspective on the networking issues, and Media Technologies Lab, we have perspectives on using video and audio as a sensor source. But prior to Huawei, I had some experience with Internet of Things, starting first at Sun Microsystems in the early 2000s, where Sun was all excited about the Internet of Things as the next wave of computing back then. And we spun up some R&D in sensor networks. And then I moved to Xerox PARC, and I was the head of the ubiquitous computing research area there. And ubiquitous computing was a term coined at PARC by the head of the computer science lab there, Mark Weiser. And it was the wave after personal computing. So the researchers there, they'd invented the personal computer, which they loved, but they found it also confining because they were shackled now to the desk and they wanted to move around the building. So ubiquitous computing was their vision of the next wave, which involved both mobile devices, which we all have now, and embedded devices. So at PARC, we did things like we instrumented all the offices, to try to optimize the HVAC, and we connected all of the computing devices and displays so it would be easy to interoperate as you move from one room to another. And that was done sort of before I had come to PARC. By the time I got there, smartphones were starting to take off. They weren't, the iPhone wasn't out yet, but the point is that the hardware problems had been pretty well solved. But what we discovered was now we had to manage all these devices, and there was all this data, and it was a big management issue. And so then we started leveraging that data to identify patterns and see what the users, what actions they would take that we could predict, and then proactively provide them information or take actions on their behalf. So ubiquitous computing there turned into sort of behavior modeling. And if you look at the bottom left here, those are the stages that I've seen UbiComp go through that I think we're also seeing in Internet of Things. First off is getting the data at all, making the computers aware of their context, their environment. And that was the first wave in UbiComp, and now we're sort of in this phase where we've got a lot of data and we can do behavior modeling and sort of we can measure the distance a person is from their normal pattern and then anticipate what their needs are going to be. And then the next wave that we foresaw there, and I don't think we're fully there yet, is to try to infer what the user's goals are, not just what their behaviors are, but what's their ultimate achievement that they're trying to reach, and proactively provide information to serve those needs. So at PARC, it was very much consumer and user-oriented perspective, and I realize this workshop is more about industrial internet, but I think a lot of the similar lessons apply. So if we go to the next slide. So this is my slide for the NSF. This is my proposal for the NSF's research agenda. I think these are the 3 categories. Yeah.
There you go, Renata.
Yeah, there you go. Well, that's what I thought about when I was putting this slide together. So I broke it into 3 categories. One is enablement challenges. I think there's certain things that have to be cracked before the grand promise of Internet of Things is even viable at all. First is power, and I have no background there, so I have not much to say, but obviously we don't want to wire all of these devices, and batteries have finite power. Even if we extend it, it's finite. And we want these things to be online forever, if possible. There are some wireless beaming power technologies that look promising, so NSF should look into those more. The next problem is not so much a technical challenge, but a business challenge that I think a technical solution can help alleviate. One is that most of the IoT use cases are sort of small. So there's a long tail of big value, but there's a lot of siloed point solutions that create that big value. And that's fine. There's big business to be had there, but what we want, though, is for all of these point solutions to be potentially interoperable so that if we identify a value from integrating them, it's easy to do so, that the businesses will be motivated. If they become motivated to do so, we want the interoperation capabilities so that it's easy for them to do so. And I think the interoperation can be solved both with protocols. Network protocols is the common way, but also think about new techniques like using mobile code to let devices learn what each other's capabilities are and be able to interoperate. Better artificial intelligence. We've seen so much advance in machine learning and recognition techniques that a lot of people are starting to believe that data-driven AI is possible to solve the big AI problems. I'm skeptical of that because we haven't seen machine learning or data-driven AI solve a lot of the problems around like planning and problem solving that we want the systems to do. So investing more in those less promising AI technologies is where I would put my money. So the networking challenges, security of course is a big one. There's various ways of tackling that, but we can't just use perimeter security for these devices that are scattered throughout the environment. We need other techniques like packet level security. The architectures for the devices needs to scale massively, and we've seen several proposals too. I think we can't have any one FOG architecture. There's going to be a variety of them, a collection and hybrids of hub and spoke architectures plus mesh network architectures. And we want them to be as self-organizing as possible so that we can reduce the installation costs. And I know this has been a research area for a while, but I haven't seen it completely cracked, so I think that's still worthy of research attention. And then the last category is about acquiring unstructured data and making sense of it. And we've seen a couple of people have already mentioned the video as a source of data, so I won't belabor that point. But you know, the challenge with it is that, well, the human eyes ingest like 83% of the information we consume comes through our eyes, another 11% through our ears. So almost 95% of what we use to estimate the state of the world comes from our eyes and ears. They're very powerful sensors, but we also know the problem is that they're ambiguous and sometimes wrong. So we need to characterize the error function of whatever we're extracting from these kinds of sensors and then propagate that through the network so that the error isn't lost when it's needed at a later stage to resolve or refine the confidence of whatever's being perceived. But I just want to reinforce that. I mean, this is a powerful source of data, and we just need to design systems that can use the content of the data streams and identify, make some semantic sense of what's in the data stream in order to contribute to the knowledge that this whole pervasive system is generating. All right, so I think I went long.
Hello. I'm Renata Rawlings-Goss. I'm at the NSF now doing big data things. So before this, I'm a AAAS Big Data Fellow at NSF, and I came from UPenn doing human genomics and bioinformatics and biophysics. So my background is in big data because that's just coming through all of the labs. But now at NSF, I'm in the computer science division in the directorate in the front office of the computer science directorate. So a lot of the big data program is also in computer science that is co-sponsoring some of the IoT, but also the big data grant. And so I would like to thank Bo for leading right into the research and being a perfect lead-in. So what I've been working on is several projects, but one of which is a big data strategic plan with the federal agencies. So a lot of there's 19, NIDART is a group, there's 19, oh sorry. Hello, so there's 19 federal agencies in a big data senior steering group that fund big data research and development. And the question is, what is the roadmap forward in big data? And then also, as an extension to that, I'm looking to you, to this group, for the roadmap forward for IoT. So that's going to be the end goal of this. But for big data, a lot of the things are going to be salient for IoT. And I've heard them here. So I'm co-leading the writing team on that particular document. So NASA, DHS, NSF, NIH, USGS. So a lot of data and a lot of different data sources. And the things that really come out are things that I've heard. So things, data analytics, the future of different types of machine learning and AI, Internet of Things. Also data to knowledge to action. So I heard action come out. And how do you quantify in that action trustworthiness, uncertainty, things like inference. How are you going to do that for big data? But then again, how do you do it for IoT, which may not be the same? And then also data privacy, security, ethics comes in there, data integration, having the right infrastructure, cyber infrastructure to make these things happen, and also collaborations and partnerships, and how do you work out those different collaborations. So these are things that are on the mind for how you deal with data, and they're questions that are still open and very much in the field of IoT. IoT is going to have all of these things, I think, and also some other things. So how you deal with these particular topics is one thing of interest, and what are the things that are unique to IoT that is separate from having data that's not quite as distributed and on all of these different sensors and distributed all over the world. So that's one thing. Also, for the IoT workshops, that leads right into these series of workshops, is really get to design that IoT is in so many different spaces, industry, health, smart cities. What are the things that are common and pervasive between all of these topics, and what things are really topical, that are really an issue that is salient to the field that you're in? And it's not necessarily cross-disciplinary, but really salient to the field. So that's one thing that's of interest to NSF, particularly as an outcome of these workshops. Also, there's a lot of work on coordination. So there's programs right now for big data regional hubs, and that's in progress. And the idea would be to have 4 regional hubs in 4 different areas of the U.S., so the Northeast, the South, the Midwest, and the West, and to try and coalesce some of the resources and people and partnerships that are in these different regions to really work together to make solutions happen, connections happen, work on priorities and national issues that couldn't be done through one institution or one company. So it's not just academic, it's academic, industry, local governments, national governments, to work together in this way to really advance things in big data. And I consider IoT, it has its own thing, but there's a lot of data involved in IoT. So that's the whole focus of this workshop and series as well. So really, that's why I said they're gonna put you to work after this to try and think about some of these things, but also just in the broader context of research and the broader context of the computer science community, we're also looking at data talent and education. That's also in there, so that you need the workers, the managers, but also the defining of the field. What are the core tenets of data science? What do people need to know? Is it very field specific? Are there some fundamental things? So there's also work in different workshops that we're considering to look at defining the field of data science. Is it not just, and the 3 tenets we're looking at now is computer science, statistics, but also social and behavioral science. Because a lot of things about data deals with people, and it deals with environment, and it deals with things that computer scientists don't always think about, and statisticians don't always think about in their design. But I heard trusted, actionable. I heard a lot of people say the words trust and value since I've been here. And those things aren't things that are necessarily written right into code. Those are things that come from dealing with the societal issues. So I'll stop there, and if anybody has any questions, then.
All right. Can you hear me? Excellent. Steve Dennis from the Homeland Security Advanced Research Projects Agency. It's like the Homeland Security DARPA, except it doesn't have as much money. Basically, we have some visionary goals that are really driving the work of science and technology, and I apologize for the laptop, but I brought them up so I don't forget it, to say something. But we're working on screening at speed, trying to make security match the pace of life, and trying to get to a trusted cyber future, which I think is a big element of what we're talking about here. Getting veracity in your data will have to do with understanding that you're actually getting information from the right sensors. 80% of the nation's critical infrastructure is in the hands of the private sector and others, and so we don't control that. I think the Internet of Things is playing a big role in the security of those systems. It will play an even bigger role as we go forward. And I think that we can get a lot of lessons learned, as was mentioned from Intel and others, about applications that are going on in the industrial area, because there's a lot more money for doing the research and figuring out what actually works in that space, and then being able to translate from the industrial space into other areas of security is something that I think would be a great efficiency and economy for Homeland Security. We're also focused on enabling the decision maker, and our tagline is actionable information at the speed of thought. And my response to that is sometimes, well, your first thought's not maybe your best, but I do think that we want to recognize that there are windows in which we can make decisions, and there's a time frame for making decisions, and that happens in Homeland Security all the time. I can't wait 16 seconds sometimes for a Hadoop cluster to spin up and get through its overhead to start answering my question when I needed the answer in 16 seconds or less, right? So that's a problem. Responders of the future, we have this tagline that says protected, connected, and aware, and you can imagine that context makes all the difference in those environments. If you're a fireman in the middle of a very smoky burning building, you're going to need to get a different form of information than someone showing you a graph and maybe a map. You're really going to need to know something like go left to exit the structure, or your victims are located to the right of you. These are the kind of things that we're thinking about in terms of outcomes for the Internet of Things. So it would be understanding your own performance as a human, understanding your physiological response to the environment, but maybe also measuring the environment to see, is that environment safe, am I protected, and making sure that everyone around me and my team understands that is important. And then getting to resilient communities has a lot to do with sort of what we call disaster-proofing society. That could either be moving to a new norm or understanding the state of resilience of a population, as a disaster unfolds, or maybe just in general, understanding the resilience of population. And there are a lot of metrics that need to be evolved there. There are a lot of different types of sensors one could use to get at that kind of information. So these are some of the big goals that we have for science and technology. Underlying all of those goals very clearly, as I'm talking, are big data concerns, and how you bring data to bear safely around those topics is important. And an immediate extension, though, to the context of those decisions that are going to be made with big data is the Internet of Things. And so some of our specific concerns, and we've started to make investments in what we were calling privacy protecting data analytics for the Internet of Things systems. So how do you get information and maybe in an aggregate sense, or without divulging somebody's identity incorrectly, is the goal of that. Maybe there are ways to temper sensors at the edge so that they can't possibly reveal information that shouldn't be revealed. Endpoint security and attestation for devices, really, really important for us. We need to understand that our systems aren't being co-opted in a security sense by some sort of enemy or force that's trying to work against us. And I remember at last year's MIT Internet of Things conference, there was a lot of talk about algorithms that might be able to work in the face of having maybe 20 or 40% of your sensors in the hands of an enemy who's trying to give you a false impression. Those kinds of areas of research are important. Methods for dividing analytic workload across this space are very important to us, keeping the computation at the edge where necessary, only communicating information that is needed, keeping it encrypted when the data is at rest, keeping the data encrypted when it's in motion, making sure that you have these policies that enable only the appropriate end users to gain access is very, very essential to what we're doing. It was exciting to hear about the DOA architecture, because I was just saying 7 years ago I saw that architecture and it was fantastic. It was one of those things where you see the design and you say, oh, it's theoretically wonderful. It'd be great if that could be part of the internet. How's that going to happen? And I don't think it's until involvement of companies like Intel that things like that can really get off the ground. So it's very good to see that. Being able to adjust your policies on the fly is important to Homeland Security. You don't want the answer to a counterterrorism problem to be, well, it's going to take me 3 years and a government integrator. That can't be the answer, right? You really do need to be able to shift the systems to respond to policy changes when they're warranted. And then I think that there are a lot of technical and architectural issues with data flow and efficiency. I've been thinking about something I call progressive analytics, where if I have mixed latency networks and only 20% of my nodes have refreshed and my data is only that fresh, what kinds of decisions can I make in that time frame? Is there a way for the system to actually tell me if I wait another 3 minutes, I could have 40% of my nodes? Getting a sense of the performance of the system and its state, and having that be available to an end user who doesn't understand statistics, but would understand that if they could wait to make a decision, the decision they make could be better, is something that we care about. And then, as a parting point, I'll just say all of this is very technically interesting. I'm very passionate about it. I think there's a lot of pent-up passion around the Internet of Things. People have been wanting to do things for years that will soon be available to us. But there are a lot of policy implications for systems like this. We were hearing that enabling the technical control of policy is one thing. Actually making the policy decision is another. If you're in a position to make policy, then you're probably making yourself responsible for something. People don't necessarily like that, but I think we need frameworks that help us, take responsibility for those policy decisions that need to be made. And so, we're working with NSF and others on these policy decision frameworks that might help us as these systems become more complex, so that we can get to the point where people understand risk and they understand liability. I think that's very important.
Thank you, Steve.
Sure.
I'd like to build on something you talked about, kind of the organization of data and computation and other things, what is done on the edge, what's done in the cloud. Particularly curious, the other panelists, if they have a perspective on how IoT might be or should be organized regarding data computation.
So maybe one quick comment I'll make here is that we talk about the data and we talk about sort of standards for integration of the data. We talk about where the computation on the data is going to happen, but there's always sort of two sides to the question that I think about. There's the data and then there's the questions, right? And we sort of think that the questions are going to come, ad hoc from some analyst or just on the fly, and just whatever they might want to come up with is something that we can answer sort of on the fly. But I think reasoning about those questions carefully and sort of doing question integration as important as data integration is something that will help you answer some of the questions about architecture and so on. For example, if the space of questions are things that are not possible to sort of push down into the edge, for example, aggregations and so forth, you can sort of push these things down quite well. Other kinds of statistical models that you're sort of trying to build, behavioral models, really do kind of need time history of a variety of different modes. That might help you make decisions about architecture, but we tend to give less attention to actually modeling and articulating the kinds of questions we want to ask. What are the space of questions we want to ask over this stuff?
Well, that was a very well-reasoned answer. I was just going to give maybe sort of rules of thumb that I've operated on in the past, is that if you could turn the sensor into a switch as opposed to a data source, that's usually lower bandwidth requirement in the network. So as much as possible, you try to do that. And if you can't make it the switch, then at least have it convert its sense data into features rather than the whole stream.
Mm-hmm.
And you can't always do that, though, because sometimes you don't even know exactly what you're looking for, especially with video data, which is very high bandwidth. So as much as you can, featurize it on the device itself, but have some back channels so that you can get the full data source later on if you need it for further analysis.
I completely agree. I think that's spot on with the
the architecture needs to be flexible in order to accommodate the question. And the ideal thing, I think, would be to have architecture that can accommodate questions that require the edge and require aggregation, and being able to switch between the two a little more seamlessly than is currently happening.
Other questions from the audience? Sorry.
I think the term you just used a moment ago was de-architecture. And the question I have for the panel is, do you see a monolithic architecture for IoT? Or is the variety of uses so broad that we're hoping that there is, let's say, 5, 6 dominant architectures, and maybe sort of the next level thing above IP that ties everything together?
Probably more the latter.
Yeah, I think more of the latter too, and I was mentioning in one of the table discussions yesterday that there's some networking paradigms like, it goes by various names, but one is content-oriented network architectures, information-centric networking, or named-data networks, where the network becomes sort of just a big distributed hash table, and devices are emitting their data, but the devices don't need to be aware of each other's IP address. We don't need point-to-point connections. We can just flood the sort of symbolically or virtually flood the network with the data, and then whoever's interested in it will pick it up. Now that sounds like that would oversaturate the network, but with the right internal smart routing systems, you can optimize those data flows and not have it actually overwhelm the network. So that's sort of a layer above IP, or it could replace IP that enables some new network architectures that do lend themselves pretty well to these kind of data-centric systems.
Yeah, I really don't see one monolithic architecture, and actually I have a past experience with DARPA where that was tried, and it was just a miserable experience. You could tell going in it wasn't the right thing to do, but it was tried with all fury, and it just does not give you the kind of flexibility you need to answer all of the questions or get to the processing capability you would want.
So we've talked a lot about technological solutions to data provenance and security, but a lot of times these things come down to a social issue, right? Because we've known how to secure email for 30 years now, but it's still only like 20% of users, their email is actually secure. Even though like 75% believe that email is secure, it's only like 20% that is. Most of it's actually clear. So how do we solve that social problem? What things can we do to try and influence people to move to the technologies we're talking about, as opposed to doing it the easy way, just send them all in.
So, I have a thought on this. The social part of it is really one thing that we're considering for data literacy. So not just being able to read charts and graphs, but being able to understand the implications of data. And I think that's a bigger thing than just having people being able to necessarily compute a confidence interval or something. But if presented with this difference between perception and what is real, that 75% of the people feel that their email is secure and private, yet only 20% is. So I think that's really a data literacy issue that could be solved that way, but that's, got a broader, more national type goal of actually educating people for that thing.
I want to comment on that because it's come up with every kind of project I've ever done, and a lot of my projects are very end-user focused too. So it's an immediate concern. But I like what Steve Orr said last night. The expectations do shift, and what people tolerate and won't tolerate shifts based on their trust of the system. So I think we all accept that. And one advance that I haven't seen done that I think could be promising, worthy of NSF investment, is to find systems that can show me as the end user who's using my data and for what purpose. Because for the most part, I probably don't care. I don't really mind if advertisers use the data on me. Yes, they're irritating, but it doesn't really put my finances at risk. And, you know, in our face-to-face interactions, we do have a sense of what image we're projecting and how people are perceiving that. And if we think that we've put ourselves at risk, we have mechanisms for repairing that damage. But in the internet, we don't know who's seeing what, and we have no way of repairing whatever faults may arise from it. So that would be great.
One other quick thing I'll add is that I feel like computer scientists are sort of addicted to all or nothing solutions, right? If we're going to take this sort of security question and say, oh, well, we'll sort of build some mathematical model that proves yes or no either is completely secure. And it turns out that all the sort of formal results in this space are negative. You can't really actually protect anything at scale. And of course, that's not actually how the real world works, right? When we buy locks for our houses or alarm systems for our houses, it's not like we invest so much that it's locked down like Fort Knox. We sort of trust that there's a police force out there and there's enough of a deterrence where, you know, if something happens, we'll go on. So I think we need to sort of think about a research agenda that includes the social, sort of socio-technical, legal, all three, and design systems with all three sort of up front, as opposed to kind of taking the pure technical problem and then failing to solve it and then sort of throwing up our hands and letting other people kind of figure out the more practical solution. So it comes up in science a lot with like healthcare type of stuff. You know, you don't have arbitrarily powerful adversaries trying to break in and do arbitrarily bad things. You have doctors that are trying to do the right thing. They just might need a warning popped up if they're joining two data sets they're not allowed to join, where they have to put in a little statement about why they're connecting those data sets or something. So, you know, trust but check or something. But building that in as a first class rather than leaving the medical informatics people to sort of figure it all out themselves, it could be a first class computer science problem, but we don't tend to think of it that way. So that's, you know, I think you guys had the case you talked about Xerox PARC. I think we're way ahead of the game in that space, and I think there needs to be more of that.
You mentioned there were three pillars that you thought of: computer science, social, and statistics. But I was wondering, is there really a fourth to study the physical, bringing in the physical scientists with this? Because we were talking, Peggy, you know, she brought up, if we have garbage, it doesn't matter what analytics we do, and also in the farm too. You know, if we're not understanding what we're doing data science on, then they will come. So maybe those four things could work together in an NSF program. Anyway, it's open to the panel that specifically can run that.
Definitely, yes, because one of the things in the education is really broken down into these core data scientists, data science that needs to be really attached to people with domain expertise, that really knows the field and the space that this data is operating in, and really what the implications are of the data. And I think that's key. We've seen that a lot in the big data solicitation. Right now we have all the other directors at NSF and other agencies partnering because there's so many different angles. So we have people from geology and data science, bio and data science, and we're required to be a real partnership, not just I'm going to do all of my computer science and then I'll check it at the end with you know, somebody who knows something about the problem I'm trying to address. You know, that doesn't work.
No.
Because you build a whole system that's not useful to anyone because you didn't think about the policy or the reality of the data or the implications of the certain things that came in. So really integrating the domain and the field expertise right up front from the architecture standpoint, like right when you start, is a way to make the thing useful in the end and to really get feedback. So.
Well, I want to make a very important distinction between application field and sensors, because my question was, directed at the sensors themselves. Because if you don't understand the sensor in the physical environment, you get garbage.
Mm-hmm.
Yeah.
I work in MEMS. Our accelerometers, they're giving you an acceleration, but that's really not what you need. You know, it's the interpretation of that. And so I think we need both application and physical understanding of sensor outputs and data and how that plays in.
So you mean the glue, whether it's still attached to the actual environment,
No,
what's the actual
No.
environment it in, and the
It's
section.
studying the sensors and the physics.
Mm-hmm.
Yeah.
I hear a lot about cyber physical. I hear a lot about the cyber and not enough about the
Yeah.
my little soapbox.
Those two worlds don't like each other.
Don't,
Yeah,
they
yeah.
don't really talk.
They don't talk, yeah.
And one of the good things is that they're starting to talk.
Yeah.
So we have, you know, a whole division on cyber physical systems at NSF, and it's, you know, on the same floor, right next to the big data, which is in IAS, which is intelligent, intelligent systems. And so I definitely agree. I think that without that understanding of the physics, you can run into a lot of issues, especially on platforms like IoT that are going to have a lot of
different types involved.
What she's saying is you can't even measure it.
Yeah.
I mean, unless you know, what you're trying to, before they didn't measure your heart rate correctly because nobody knew how fast to sample and what it really, and so it's one of those things that you have to have somebody who knows the environment to say, yes,
Or-
you actually want to.
These magnetometers that if you go by a magnetic field, you're toast. So the magnetometer is reporting it's, but it's not the right thing. So all I'm
Yeah.
saying is we need a lot of physics involved, also the computer science and the social statistics. It's all one big problem.
Yeah, but I think that is definitely a big problem, but it's coming, I think, it is lagging behind. Well, it's not behind, people are working on it, but it's not wrapped up because this data science question isn't wrapped up yet. Nobody's got their head fully around it. Yeah.
Thank you. Should be a question, and one more after Chip.
So I think I'm obsessing some more about policy, but I'm going to come back to that. So as an example, I have an iPhone and I can, by application, say enable location tracking or not enable location tracking. But it's a binary decision that I need to do it or not. And then in circumstances where I might want to for some particular reason. And so that means that the options I'm being given aren't captured in the universe in which I would really like to operate. And I think that, what I would really like to be able to do is that under such and such circumstances, yeah, please use my location, but in other cases, no. So that sort of seems to be policy-driven data analysis or data capture even. And I think I asked Peggy the same related question, and if I interpret Peggy's answer correctly, there's some interest, but there really isn't a cohesive plan of action around it. So my question to the panelists is, are you aware of a cohesive plan of action around it? And then the follow-up to that is, if there isn't, then there's something for NADA and NSF to consider that. That I think that there is a real value to be had by trying to understand how to get policy down at all levels of data.
So maybe real quick, just what comes to mind when you're talking is maybe two things. One is the problem, especially in the consumer space that you're mentioning. I think the real challenge is that attention span is a limited resource, right? And so no matter how much control and power you give people, no one's going to bother to use it. Whether you set it up with complex sort of event condition action kind of rules about how you control your policy, nobody will bother doing that. And if you start prompting people with, hey, do you want to allow this and this all the time, they just click OK as fast as they can, and they don't really care about this. So that's maybe on the bad side. On the good side, it may be a model that I see. This is maybe a strange example to bring up, but if you look at like Amazon Web Services, there's a really complex set of permissions you have to kind of do when you're allowing people in your organization to sort of do different things. And there's all these different services, and they all different things. And they've got a little permission language, right? And you can write these very complex things. And one thing you sort of see is that people are sort of sharing their permission scripts, if you will. So sometimes the trust is not so much that I'm going to scan through this and really make all these local decisions for myself, because that requires too much attention span, even for a company. But I can borrow somebody else's. I trust them to sort of come up with some kind of a reasonable set of frameworks. So off the cuff here, I'm imagining that you might be able to do the same thing for, say, Facebook or Google or IoT, where I don't really have to make all these individual decisions, but I trust you, that you put a lot of thought into this as a researcher. I might just borrow your set of policies and apply them to my Facebook account or something. Might be one way out of this quagmire.
So what you're saying is that there should be a social ecosystem around this. Everything you said is around building a social framework.
This makes sense. I mean, the rules are going to be complex, and to manage that complexity, you probably need some sort of a trust network among people that have thought about it more than you.
Other panelists have a point of view.
Yeah, I'm sorry.
I mean, I think that bottom line, I would just agree with it. It is a big social kind of policy issue. And I've seen research projects in both the security community and in the HCI community, human-computer interaction, about managing complex privacy settings. And there are solutions. I think most of them fall into borrowing, models of sort of types among people, because end-user programming of security preferences is just too complicated.
So there actually there's another strategic plan on privacy research that's going on. And we had a workshop where this came up. And some people were actually working on the fact where they did a pilot, where they gave people more options. And the thought was they wouldn't do it, but they did. They ended up using that model and actually taking the time, if you don't give them 10 million options, to say yes, no, maybe in some sense. So I think in some sectors that could be a viable option.
Maybe I'm just projecting my own apathy or something.
All right, one last question. Becky, hang on.
So I was gonna ask, oh, okay, just a second. I'm wondering, in terms of even applying it to what you just said about the policy, we're spending a lot of time on, people want it, it's the way that they have to do it today that's the problem, right? Going and scanning 5 million, well, it's not that they don't want all that set, it's that they don't want to scan them, they want to know that something learns about them and says that their policy settings for that person is X, Y, very, very high, and okay, it's laxing off of getting to know one person. So you're seeing that a big part of it as well is just the barrier for people to the way they interact with technology is what's preventing those things from happening, not that they don't want them. Do you think there's, because what I see is that people, end up correlating, oh, they don't want that because, yeah, they don't want to go through, none of us want to go through that. I don't even like programming it. Nobody wants to do all that on either side. Do you think it's, because I look at analytics and learning somebody's behavior that then applies their policies, right, based on understanding them. Do you think it's a lot about the human-centric side as well, that influences what ends up happening?
I mean, I definitely do. I think that that's what that study really came up with. It wasn't that people will click yes or no because there's only a binary choice. And you're basically saying, I will not have the convenience of this app or this thing that I specifically downloaded already unless I click OK. And that's it. I'm just going to suspend my disbelief and click OK because there's nothing I can do about it, right? It's either yes or no. Why read the thing? But it turns out that, people do want some choice. The question is how much choice and how, and then the issue came back that if somebody changes their choice and you've done all this data aggregation and Internet of Things, how do you actually go back and say somebody wants to opt out late in the game? So there's a lot of issues that can come up through that, but I think that it's not that people are just totally apathetic to
I think it's a very nuanced, very complex issue. So another perspective is that I think the way we're managing privacy today is not really the way we do it in real life. And what I mean is, in real life, we try to project a persona, an embodiment of certain principles or something like that. But to manage my data privacy, I have to say, I don't want to share my location data. But that's not the way I think about it in real life. What I'd like to do is say more like, I want to project the image of somebody who doesn't go to comic book stores or something like that. So there's higher comic book stores. Actually, that's too fine-grained too, right? That's too fine-grained. I want to project the image of a respectable adult, right? That's more like what I want to say. And then have the system figure out how to implement that. That would be another approach to handling it that I think would be acceptable and manageable.
That's great.
So I think most one of the common Special thanks to the panel for your time and insight.
Thank you.
They'll be around the breakout session this afternoon if you have follow-up questions. Thank you.
Thank you.